Just look at the limit. So we want VCA, and we say it's VC minus VA divided by 1 some sign plus minus VC VA, right?
Yes.
So you want to see whether it's plus or minus.
Right.
The first of all, the numerator is the fact that here is VC minus VA is just the same. You can guess it from Newtonian limit,
yes.
Non-relativistic. The relative velocity is the velocity of Charlie minus the velocity of R. So this minus sign is just from the non-relativistic limit. This sign can be determined by the ultra-relativistic limit. So take the limit that one of the velocities approach the speed of light, and use the fact that that's the speed of light is the ultimate velocity, so nothing should become larger than that. Okay, so let's see. We want to take, for instance, say if I take VA to 1, because C is set to 1.
Yes.
Then, or if I take VC to 1, in both cases it has to limit 1.
Yes.
Because the velocity of light is also absolute.
Yes.
It should be the same in all
frames. Yes.
But then, so it means that VCA, if VC goes to 1, has to be 1, and that fixes the sign, that fixes this sign to be negative, right?
Yes.
Okay. Other questions?
In the case, I mean, for example, if in the case that you want to compute the proper time of say our line, you try to compute the proper time like parameterizing the trajectory with some parameter.
Yeah.
Can you give us maybe an example of how you can parameterize the world? I mean, in the I don't know, in a way a proper the trajectory. I don't know, maybe using the proper time or maybe using another variable, something like that.
You want an example in which we parameterize the trajectory using proper time or using some other variable?
Maybe some other variable.
So today we will see an example of how the trajectory, the world line is parameterized in terms of the proper time. In the yesterday's example, we had this constant velocity motion, right? So we were saying that there is this trajectory, which is a world line with velocity VA. So we said that x is equal to VAT, or XA is equal to VAT. I have already given a parameterization of the world line when I write this. What's the meaning of parameterization? Is the finding some. So if I want to write it mathematically, I think parameterization is a map from R or an interval in R to your manifold, in which case it is a two-dimensional Minkowski space. So there is some x mu of lambda is a function of a parameter that lives in R, and then for any value of that parameter, it assigns a point in the manifold, which is, in this case, this. So now our parameter, when I write this, that is immediately a parameterization of this curve, which is is basically T and BAT. So think of lambda in this particular case. Lambda is actually T. And then when we say that the proper time of all this is T over gamma A, plus some constant, you can easily trade T with tau, so you get a parameterization of the curve or the word line as a function of proper time. So it's nothing fancy. We always do it.
You have acceleration. You can write the acceleration. I mean, you have to solve first the acceleration as the solution for like the differential equation, and then put it like in the word line.
Yeah, well, what I'm saying is that, of course, the solution will be different. But what I'm saying is that whenever you solve some dynamics problem and find the trajectory of some projectile as a function of time, you are parameterizing the word line in one way or another. So we will see in the accelerated case another example of.
Because, for example, in order to do that, I mean, x equal to vt, you are like solving in the case acceleration is 0, and then you are like solving I mean, intrinsically you are solving that, and then you're saying, okay, x is equal to this. In the case of the in case of the acceleration is not 0, then you have to solve another differential equation and then parameterize that equation. I am asking you can do it also like solving like in the Newtonian case and use it to parameterize the relativity.
I'm not sure if I understand the question.
It's because, for example, you cannot use like x is equal to 1/2 of 8t squared, because I guess you could get velocities maybe greater than the speed of light using that. So then you have to solve another equation to get the correct expression of the coordinate x with respect to time.
But yeah, that x equals 1/2 AT squared is a Newtonian answer for a constantly accelerating object that doesn't hold in relativity.
In relativity, you have to use.
But that is a dynamical statement. It doesn't have to do with parameterization of a line. So that's basically the statement that there is some maximal velocity, which is the speed of light. So any word line that you want to draw here, that cannot. It's a slope. Maybe this is too fast. The slope of any line that you draw here cannot exceed, cannot be smaller than this 45-degree line. Now you can have different forces or different dynamics that that is consistent with this property, but gives you different acceleration. And then for those you will have different. I mean, depending on what is your dynamics, you will get a different answer for the word line. Before I tell you what is the dynamics, you wouldn't be able to find x of t. But of course, the Newtonian dynamics breaks down. So there should be a relativistic version, which we are going to discuss.
Okay.
Okay, so yesterday we talked about Poincare transformations, some set of coordinate transformations, which preserve the speed of light. So now today we want to talk about dynamics a little bit in a special relativity. So the main principle of a special relativity is that the equations that describe physics, they have to be invariant under Lorentz transformations. So when I write some physical equation, the two sides of the equations have to, we usually say that the equations have to be covariant, meaning that they have to relate quantities. So when I write some equation of physics, usually it means I'm writing an equality. So two objects, two observable are related to each other, and the principle of relativity is that these equations should look the same in different inertial frames, meaning that they have to have the same transformation property. And then the other rule that we follow is that we know we have experimental evidence for many laws of non-relativistic physics. So in the appropriate limit, the laws of physics have to agree with the ones that we have checked non-relativistic. So basically, that's how we write the generalization, the relativistic versions of the laws of physics. So today we are going to consider dynamics and see how Newtonian dynamics generalizes into relativistic dynamics. So one thing that we have is the conservation of energy and momentum in processes. So if you have some process, we know that the sum of the energy and momentum the energy, initial and final energies and momentum have to be the same, and the way to generalize it in a special relativity is that we define this momentum 4 vector, and in any process with a set of initial states going to a set of final states, the sum of these 4 vectors have to be the same on two sides. And this P mu is defined as m times u mu, where u mu is the 4 velocity that we defined yesterday. So this is a 4 vector, and this equation relates quantities which have the same transformation properties under Lorentz on two sides. Moreover, this equation has the right Newtonian limit. So if we consider particles which have small velocities, in that limit, this equation reduces to the usual energy momentum conservation that we have in the Newtonian limit. So this is one general rule. The other important equation that we have in Newtonian dynamics is the second Newton's law, which now we have to write it again in some relativistic form. So this is the equation that seems to be what we have to write, because now we need to relate acceleration to some force. But now since this d2 x mu d tau squared is a 4 vector, then here we have to put a 4 vector. Now in order to agree with the Newtonian limit, what we should require is that when we take the limit, when we go to the rest frame, meaning that when v goes to 0, then this equation has to reduce to the Newton's equation. So it should become m dv d tau equals to F Newtonian. And therefore what it implies is that if the Fi components, the spatial component of this force vector in the rest frame have to be the same as the Newtonian. Now we can ask what is the zeros component. So as we said, this F mu is a 4 vector. So there is some F0. Let's look at it in the rest frame. There is F0 rest frame. And then here there should be Fi Newtonian. So one thing to determine is what is F0 in the rest frame. So that is easy to determine, because if you look at this equation is basically m du mu d tau, which is equal to F mu. And now let's remember that in the rest frame, u mu is just equal to, so in general u mu was what, gamma 1 and v, and therefore u in the rest frame is just 1 and 0. Now if we also know that u squared, which if you remember is just eta mu nu u mu that is equal to -1. So if I take the derivative of this u squared with respect to tau, that has to be 0 because it's a constant. On the other hand, this is so this is 0, but it is also equal to twice u mu du mu d tau, which from the definition of the force, it is given by twice u mu over m times F mu. But now if so as you see, this is a scalar quantity, right? All indices are contracted with each other. Therefore, it can be evaluated in any coordinate system. In particular, it can be evaluated in the rest frame. So I can look at u rest frame mu f rest frame mu. But u in the rest frame is just 1. Has only 0 component. So that is equal to -2 over m f rest frame 0. So this has to be equal to 0. Therefore, we conclude that this is 0 and F5 Newton.
I have a confusion.
Yes.
If we did the derivative just, I mean, if we had the u of rest frame, if we take the derivative with respect to the proper time right there, why couldn't we get that answer?
So say it again. If we take what?
I had the u mu rf in the rest frame, yes. If I take the derivative of this and multiply by m, I should get that, right? Why did I have to do this?
Well, the rest frame is some time-dependent notion. So when you, the rest frame itself is not some, so imagine in general something that accelerates. So just again consider some accelerating observer. So it will have different velocities, right?
Yes.
At different times, the rest frame of this observer will be different.
Yes.
So now, initially it is at rest in this original frame that I consider. At later time, there will be other frames with respect to which it's gonna be at rest, right? But there is also time dependence of these rest frames.
Okay.
Therefore, one should be very careful about taking derivatives of object evaluated in the rest frame, because the rest frame itself is time dependent.
I see. So even if it's not a rest frame, we cannot take the derivative because all other frames are also. If it were not rest frame or some other frame, could we do that? We couldn't, right?
Well, as long as you are talking about an inertial frame,
yes,
that is fine. You can do everything. Because the frame, you fix the frame that you are working, and then you can take the derivatives. But when you talk about rest frame, you haven't fixed the frame. You are changing. It's not a fixed inertial frame. It's a set of different inertial frames at different times. So when you take time derivatives, then you should be careful about the fact that the frame itself is changing with time. So for instance, if you take derivative of this, you get 0, but you also get 0 in this count.
Yeah.
Okay. So next we want to discuss the Rindler observer. An observer with constant acceleration. So this is a very cool problem. I'm going to solve it because it's very important. So what is the problem? The problem is that the bulb is moving with constant proper acceleration. And proper acceleration means that the acceleration in the rest frame is constant. So the definition is basically, if I calculate, so if I define the proper acceleration, if I define acceleration for vector a mu as f mu divided by m, then proper acceleration is basically the norm of this a vector, and it is also the norm of it in the rest frame. So in the rest frame, this is gonna be 0 and this f Newtonian divided by m, and we are told that this is going to be, let's do 1 plus 1 dimension. So we are going to consider this to be a constant. So what it implies is that if I calculate the norm of this acceleration for vector, that is going to be minus a squared. So proper acceleration is defined as square root of minus eta mu a mu. And for linear observer, we are taking this to be a constant. Now, what is going to happen? So Bob starts at t equal to 0, at x equal to 0. It starts at rest and then accelerates. Its velocity is going to increase. So this is the tangent is along t, but then it accelerates. It has a constant acceleration. We know that there is a maximal speed, which is the speed of light. So the only thing that it can do, if it was Newtonian, it would accelerate until it reaches infinite velocity. Relativistically, we cannot reach infinite velocity, so the only thing that it can do is to approach the speed of light. So qualitatively, we know how its word line is going to look like. It's going to look like a hyperbole. So we want to calculate the word line, the trajectory x of t. Okay, so let's so basically the question is that we want to see what is x mu of tau. So let's imagine at some moment it has reached the velocity v. So let us see what would be the force in that moment.
Sorry, just a question. Why is the minus there? The minus there.
Oh, why is there a minus here? Sorry, there shouldn't be a minus because I'm working with mostly plus. You're right. There is no minus. Thank you. So let's consider some moment of time, like here when the velocity is v. And let's determine what is this force for vector at that moment. So this force for vector, or the acceleration for vector, is a constant in the rest frame. But what it means is that in the original frame, it's not going to be constant, right? Because the velocity of this observer is changing with time. So if this for vector is a constant in the rest frame, it's going to change with time in the original frame. So now we want to determine what is f mu when the velocity is v. So the way we do it is that this f mu is a 4 vector, so it has the same transformation properties as x mu. So F0, or let's talk about A mu, which is just F mu divided by. So A0, which is d by d tau of U0, and U0 we know that is gamma. That is equal to A0. And when the velocity is v, that A0 is given by, is related to the A rest frame, which is, so it has so this is a general transformation property for a 4-vector. And then if I write the first component of this equation, so that will be d by dt of u1. So this is, let me just be more explicit. U1, that should be the spatial component of velocity, acceleration. And that is related to the acceleration in the rest frame by a Lorentz transformation. So everyone agrees with this equation. So in the rest frame, so here this is a mu in the rest frame. This term is 0, this is 0, this is gonna be gamma v times a, the proper acceleration, and this is gonna be gamma a. And in the left hand side, I have d by d tau of gamma equals gamma va. And here I have d by d tau of gamma v equals gamma a. And then, so this is for an orbit at some arbitrary moment when the velocity is v, we get this equation. And then we can solve them to find v as a function of tau. Once we find v as a function of tau, then we can find x as a function. Okay, so for instance, we can solve it by noticing that this is gamma dv tau plus v d gamma d tau plus gamma a. And then if I combine it with the other equation, it gives me gamma d tau plus gamma v squared a is equal to gamma a. Therefore, dv d tau is equal to a and 1 minus v squared. Any questions so far? Okay, so let's see what it does. The velocity, let's see if it makes sense. This tangent hyperbolic, it looks like this. This is -1, this is 1, this is v, this is tau. So that's how the tangent hyperbolic looks. So we start from 0 velocity at tau equal to 0. The velocity grows. Initially, it grows linearly with tau. So that's the Newtonian limit. When you have constant acceleration, the velocity grows linearly. But then it approaches the constant. And the constant is 1, the speed of light. So it agrees with the expectation. Okay, now that we have v, we can calculate t dot and x. We can calculate t and x, or x mu of tau. So first of all, t dot. By the way, I use dot for the derivative with respect to the proper time. So that is just u0, and that is gamma. So gamma is 1 over square root of 1 minus v squared, which is 1 minus this tangent hyperbolic squared of a tau. So this is just cos a tau. And therefore, if we integrate this equation, we get t equals 1 over a sinh a tau. And then we can do similarly solve for x dot. So for instance, x dot over t dot is v. Right? This is just dx dt. This is v. And this is equal to well, this is equal to this tangent hyperbolic of tau. And that means that x dot is equal to
Cos
uh,
sinh.
yes. And therefore x is 1 over a times cos a tau minus 1. So I fixed the integration constant so that at tau equal to 0, we'll start from x equal to 0. Okay, so this is the equation of motion for the linear observer, which is a hyperbola. Any questions so far? So now we can talk about linear horizon. So imagine this is So this is Bob who is accelerating away from the origin, but Alice stays at the origin. She stays at rest. So what happens is that they can communicate, or Alice can communicate with Bob until some time, and then afterwards she cannot anymore. So if she sends messages to Bob, there will be some time after which there's some time for the final message that she can send, and then no messages from Alice can reach Bob. When there is such a final time for sending messages, we usually call it the horizon. So it's like falling outside of a or going beyond the horizon. You cannot see any messages anymore. So basically, Bob, what it sees is that from the point of view of Bob, Alice is going beyond the horizon. Then there is no messages coming from Alice anymore. It's going to be dramatic. So we want to determine this time. What did I call it? TA. So this TA, we want to determine that. That's what is the time for the final message. So what is the time for this? It's basically looking at the asymptotic trajectory of Bob and see where it intersects the t axis. That would be the final time, right? So all that I need to do to determine TA is to see how this trajectory behaves asymptotic, as I send out to infinity. So the horizon. If I send tau to infinity, then t will go as 1/2a e to the a tau. I'm just using the asymptotic behavior of sinh and cos. And x will go as e to the a tau over 2a minus 1/a. So this is the same as t. This is equal to t minus 1/a. So the intercept of this trajectory with the t-axis is just 1/a. So ta is equal to 1/a.
The proper time is the time of the clock of the person, I mean, of someone that is traveling with that port line. Yes.
Yes.
So in that case, we can talk. I mean, we can talk about the proper time as the time that pass. I mean, that is passing in the clock of that traveler.
Yeah.
Since from a certain reference frame. For example, you put your at the origin and you and you can compute the time that is passing in that word line by computing the proper time. My question is that, for example, in the expression of the velocity, if you would like to express the velocity in terms of your time, then the proper time, I mean, is related with a factor of a gamma, but the gamma will carry also the velocity, which has also a factor, which is also function of the proper time, which is also function of the time and the gamma. And
if you are referring to this relation that we wrote yesterday for relation between t and tau, which was related by gamma, that doesn't hold in general. So this is what is true is this relation. This is always correct. dt d tau is always gamma.
Yeah,
but t as a function of tau is not just gamma tau. Like here, the relation between t and tau is different, right? Now, if you want to write the velocity as a function of t, so I guess your question is that what is v of t? It's a good question. I think we have all of the information on the board to answer this question.
It's just using the t there and using that.
Yeah.
Okay.
Basically, we need to invert it on something. Okay. Other questions? Okay, what's the final thing? Finally, I should talk about the redshift. So imagine Alice is sending messages every second, so one message per second. So we want to ask, with what frequency does Bob receive messages? That is kind of one way of asking about redshift. Another way of asking about it would be that imagine Alice shines a light towards Bob with a fixed frequency in her rest frame. So she has some laser pointer and points it towards Bob. And then laser pointer has some fixed frequency when in the rest frame of the pointer. So it's like it's a red point. Then Bob receives this receives the photons that are sent until some time. We want to, but he receives them with possibly different frequency, and the question is what is the frequency of those photons. These questions are all equivalent. You can ask what is the rate of receiving messages, or what is the frequency of the laser. that she receives. And if the frequency decreases, we call it redshift. If it increases, we call it blue shift. Okay, so how do we answer this question? We can, and one thing that we can ask, now here we have all of the ingredients to answer even a more elementary question, maybe, or a slightly different question, which is that imagine I send a signal at some time t emission. We can ask at what time that message arrives to Bob. So we want to determine what is. Let me draw another picture. So there is this trajectory. There is a message sent at TE, and then it travels with the speed of light. So it crosses Bob's trajectory at this time, at this point, and we want to see what is tau corresponding to that. So why is it useful to know that? If we know tau as a function of T emission, then we can ask what is the difference in the value of tau for two messages. So we can determine d tau as a function of, or we can determine d tau by dTE. And that is exactly the redshift that we are interested in, because it tells me if I send messages every 1 second, what would be the frequency that I received in the Bob's space. Okay, so what is the arrival time of this signal? So this signal, it travels at the speed of light, and its equation is so it has some non-zero intercept. The slope is 1 since it travels with the speed of light. So x is equal to t minus te. So at t equal te, it is at the center. So that's the signal. And that's the line. And then we want to intersect it with the trajectory of Bob, which is this. So that tells me that TE at the intersection, TE is just x Bob minus T Bob, which is 1 over A cos eta. Sorry, it's T Bob minus. So it's 1 over A sin eta minus cos eta plus 1. And therefore d TE d tau is equal to cos eta minus sin eta. And this is exactly omega observed divided by omega emission. Because frequency is related to the inverse period. Okay, so this is the redshift. That's exactly the definition of redshift. And it's given by that formula. We can, it would be nice to look at the limit of tau, tau much larger than 1. Tau goes to infinity. Then this difference is it becomes exponentially small. So let's see what it is. It's basically e to the minus 8 tau. So what does it mean? What it means is that, so as we saw, there is some final time after which no messages arise at bar. So what happens is that the redshift goes to infinity. The messages take longer and longer until they reach bar. And at some point they don't reach anymore. So that's another way of saying that infinite redshift falling in a horizon is equivalent to, or it's accompanied by having infinite redshift for the signals that are sent. Questions? Okay, so let me do it a little bit more systematically. I mean, this is nice and heuristic, but I guess it would be useful to have some more systematic way of calculating the redshift. Just thinking in terms of photons being sent from, or passing, traveling from different points, from the emission points to the absorption. So another way of thinking about redshift is to think about a photon that moves from this point to that point. So we want to measure the frequency of the photon in these different frames, or by these observers. Now, what is the frequency of the photon that is observed? That is measured by an observer with the 4 velocity u mu. So say here I have a photon with 4 momentum k mu. So since it is a photon, it will correspond to a null trajectory. So k squared is equal to 0 for a photon. But what is its frequency measured by an observer? That is basically looking at the zeroth component of this k mu, but in the rest frame of the observer. But in the rest frame, we know that the 4 velocity is equal to 1 and 0. So therefore, the frequency of the photon measured by some observer, say Alice, that is equal to minus u mu, or u of Alice mu, times k mu. That is exactly looking at the zeroth component of k mu in the rest frame of Alice. Since this is a scalar quantity that can be calculated in any inertial frame, but therefore we can go to the rest frame, and in the rest frame we know that it is just a zeroth component of K0. So that is the frequency measured by an observer. Okay, so we have this, and there is omega b, which is ub mu minus ub mu times k mu. Now, given these three equations, you can easily determine what is omega b over omega a, which is what we are interested in. Omega b over omega a is exactly this ratio, omega observed divided by omega emission. So how do we determine this? Well, one way is the following. We can derive this 4-vector k in the Alice frame, which is the original frame. So if I use these two equations, from 1 and 2, we can determine K mu. K mu is essentially omega A 1, 1. Right? So it's a null vector which travels toward positive x direction, and its zeroth component is omega A, which is the correct value in the rest frame. And what is ub mu? That we have also determined here. So we know the velocity of Bob, and we know its boost factor, so it is cos a tau times 1 and times a tau. So then we can look at we can determine what is ub mu. So let's just write dots. ub dot k minus ub dot k, that is equal to, so we just need to take the dot product here of these two, and that gives us cos eta minus sin eta, which is what we found here. Are there questions? Okay, if there is no question, that's it. So on Friday we solved the homework problems together. I asked you to come and show the solution. I can also fix some office hours, so that if you have, if you want to meet me or talk about the problems.
Yeah.
So when would be a good time?
In the morning.
In the morning. Yeah. So what about probably Thursday before the homework day would be the most useful time. So maybe Thursday morning. Say, I don't know, 11.
The class today will be at 11 always, or only for today?
No, only for today, because there are 2 seminars today that I wanted to do. I think the seminars are, this particular seminar is on once in a month. So next month probably will be at 11. Alright. Do you want to talk?
Yes. I'm coming.
Okay.
I'll join you in the lunch.
De un profesor que igual no tenía como que, no había como seguir ningún libro. Así que aprendí. Creo que es de la forma que me gusta, que a mí me gusta leer. Así que tocó aprender de sus notas.
Era de sus notas. Bueno, tenía unas notas de clase en la pero el problema es que la tarea la dejaba antes de dar la examen. O sea, la tienes que entregar antes de que diera la estaba pagada, ¿verdad? Bueno, de las notas de
I didn't do it yet. I want to.
las notas estaban horribles. Un approach muy